So now we're on section 3.4, which is our composition of functions. This is a really fun section, very technical and algebraic, and getting comfortable with the importance of parentheses, I would say, is the goal in this section. In terms of all of our learning objectives, we have 5 here. So we'll be able to combine functions using algebraic operations. We'll be able to create new functions by composition of functions. We'll do loads of practice with evaluating our composite functions and finding the domains of composite functions. And then our last part, we'll do some examples being able to decompose a composite function into its component functions. So you see this big function and breaking it up into 2 or 3 or 4 smaller functions. I believe there are about 16, there are about 18 slides in this section before we jump into our transformation of functions. So let's jump into it. Our first objective, being able to combine functions using algebraic operations. And so addition, subtraction, multiplication, and dividing are all of the operations, but from a function standpoint, if you're adding two functions, our f plus g of x is the same as just adding f of x and g of x separately. The same goes when you're dealing with subtraction. You just subtract the two functions from one another. Multiplication, straightforward, you just multiply the two functions. And then dividing, again, you divide the two functions by one another. Composition of functions is different. It's not dealing with these operations. A lot of people think that composition of functions is multiplying, and it's not. This is not composing of functions. It is purely multiplying. Composing is when you're putting a function within a function. You're not taking a product. And so f of g of x, even though it looks like multiplication, it's not. When you have the parentheses within the function itself, that's where composition takes place. Another way to represent this is that open circle, that mini circle over here, which stands for composition. But we'll practice with this notation a lot throughout this section. Before we do, let's just get more comfortable with our main operations, subtracting, adding, multiplying, and dividing functions. So if we're given our f of x is x minus 1, and we're given our g of x is x squared minus 1, and we're asked to subtract f from g in our part A, then we're essentially doing green minus yellow. Don't forget your parentheses, x squared minus 1 minus x minus 1. That way, you don't forget to distribute that negative to both terms inside of our yellow function. And then we simplify. -1 and +1 cancel out. So our final result is just x squared minus x. If you wanted to factor it, you can, but you don't have to. And then we're done. You only have to factor if they tell you to. or if they ask you to find the solutions, possible solutions of X. Yeah.
Like when they ask to simplify, does it
Mhm.
happen automatically?
Good question. Simplify in a lot of cases when you're dealing with factoring, yes. But in a case like this, this is probably even more simplified than this, right? You have only two variables here, you're dealing with three here. So yeah, I would give you full credit either way. Now, part B is asking you to divide the functions by each other. So now we're doing green divided by yellow. And then we're asked to simplify this. This is where factoring actually does help because that numerator is the difference of squares. So we can factor it into x plus 1, x minus 1, all divided by x minus 1. And then you'll notice the x minus 1s cancel out. And so your simplified result is just x plus 1. And you're done. Yeah. Yes. Mm-hmm. Objective 2 is to create a function by composition of functions. So maybe I'll have someone read these paragraphs for me. Yeah, go for it.
Performing algebra operation and functions combine length into a new function. But we can also create a function by composition functions. The process of combining functions so that the output of one functions become the input of another is now as a composition of functions.
Thank you so much. And then why don't I know I subtly spoke about this, the whole open circle and our notation, but maybe I'll have someone read up until this last pink line for me. Nor, do you want to read it for me?
All right, okay.
Let's see. Is that better?
Yeah.
Okay.
When the output is the input from of another, we call the entire operation a combination of functions. For any input x and functions f and g, this action defines a composite function which we write as f
Of G.
of g, such that
F of G equals F of G.
g x equals f of g.
Yep, good. Yeah, so again, notation. Now the second part is really honing in on the domain aspect of this. And so the domain of an f of G function is simply all x such that x is in the domain of G and G of x is in the domain of f. So we have those two conditions that we need to be on the lookout for. We have to have our x be in the domain of G, and then we need to make sure that our G of x is in the domain of f for us to analyze the domain of the composite function itself. And then once again, I know I spoke about this previously, but really try your best not to confuse the product of functions with compositions. They mean something entirely different. This is not a multiplication sign. It's a completely different rule. So maybe I'll box this in red so that you really make note of that mental note. And then here is just a visual standpoint. I personally find this to be more on the confusing end, but they're essentially saying when you're looking at a composition of a function, your f of g, you need to make sure that your values of x are in the domain of g of x, and then your new values of x, aka your values of g of x, are in that domain of f for us to analyze the domain of f of g. And that's what's being represented over here. So, and then they also state the reason is if g of x is not in the domain of f, then our whole f of g of x is compromised. It's not defined at all. Okay. So let's look at example 2. We're given both f and g, and we're just asked to compose f of g and then do the reverse, compose g of f. So we have two different problems here. I'll break this up into like a part A and a part B. So part A, we're finding f of g. F of g, also known as fog, is the same as just f of g of x. And the key is whatever you see on the outside is like the parent, and then the inside is the child. So parent is always carrying the child until hopefully they're 18 and they can be self-sufficient. But how do we do this from a parentheses standpoint? Well, we really hone in on that parent, and wherever we see an X, we draw in parentheses. So we have 2 parentheses plus 1. And now inside those parentheses is where the child comes into play. That's where our g of x goes. 3 minus x. And now from here, it's just simplification. Utilize your knowledge of distributive property, combine like terms, and then you're good to go. 2 times 3 gives you 6, minus 2x plus 1. Combine some like terms. 6 plus 1 gives you 7. So therefore, your f of g is just negative 2x plus 7. And then you're done. Part B, it switches. And now you're looking at g of f, also known as GOF. So your parent is now g, and your child is f. So let's look at the parent, and wherever you see an x in that yellow function, you're going to just put in a big giant parentheses, because what's going to go inside there is your child, which is now blue, and that's just 2x plus 1. Use distributive property. You're distributing that negative to both terms inside the parentheses. And then you're going to go ahead and combine some like terms. So we essentially get g of f is just negative 2x minus 4. And we're done. And it's not negative 4. Yeah. Thank you. Good catch. You guys are paying attention. Love it. Yep. We're almost there. 25 minutes. Any questions on this? No. How did you guys feel about this example? Good. Nice. Cool. All right. Let's keep going. So example 3, being able to interpret composite functions. We have the function C of S gives the number of calories burned completing S sit-ups. I like this question. And S of T gives the number of sit-ups a person can complete in T minutes. So we want to interpret C of S of 3. That's kind of cool. Great example, by the way. I'm also looking at these questions for the first time with you, so it's exciting for me as well. So if C of S is the amount of calories being burned and S of T is, okay, how many sit-ups can I get done in T amount of time, then what is this saying? How many calories you can burn in what? Exactly, in 3 minutes, right? So 3 minutes of doing sit-ups. How many calories you burn after doing 3 minutes worth of sit-ups? And then now we're on to our third objective, evaluating composite functions. I'll read this part for you guys. Once we compose a new function from 2 existing functions, we need to be able to evaluate it for any input in its domain. We'll do this with specific numerical inputs for functions expressed as both tables, graphs, and formulas with variables as inputs to functions expressed as formulas. In each case, we evaluate the inner function using the starting input. And then once we evaluate that, we use that inner function's output as the input for the outer function. So it's like you're evaluating something twice. You evaluate the inner, calculate that, and then reevaluate it for that outer function. Sometimes you have to do it more if you have more compositions taking place. Now, our example 4 is being able to evaluate a composite function from a table standpoint, which some people get a little confused about as first. I'll try and make it as straightforward as possible for you guys. Once you get the hang of this, though, it's kind of fun. So the first part, we want to find f of g at 3. So again, look at that inner part. When x is 3, our g of 3 gives us 2. So let me color code this a little bit more properly. So we're looking at f of 2 now. And so now when x is 2, what's our f? It's just 8. That's it. So you first want to evaluate the inner, g of 3. 3 is just our x, right? Because this essentially is g of x. Well, okay, when x is 3, what is our function? When x is 3, what is our g of x? Our g of x is 2. You got that part? And now we know this is 2 now. So now we plug in 2, and now we just want to evaluate f of 2. So when our x is 2 now, what's our of 2. It's 8. Yeah. Now we're doing the same process, but instead of looking at f of g of 3, we're looking at g of f of 3. So I'll use different colors here. F of 3, when x is 3, what is f of 3? It's just 3, yeah. And now we're looking at g of 3. So look, when x is 3, what's our g? 2, right? Because it's g of x now. So it should just be 2. And then we're done. Yeah, this one is like, you get the hang of it a lot more when you practice it more on your own. Yeah, of course. Okay. So this is just the formalized notes. If you're given a composite function and you're asked to evaluate it using the information provided by the graphs. We just did a table example, but we'll look at a graphing example in a moment. Same exact concept, it's just you're pulling data in a different manner. So here, we're asked to evaluate f of g of 1. And that first graph is our g of x graph, whereas that second graph is our f of x graph. Just color code a little bit. And so again, look at the inside. We're first evaluating g of 1. So when x is 1, what's our g? It's 3. And now we want to evaluate what is f of 3. When x is 3, we get 6, right? So our answer is 6. That's it. And these are just the step-by-step procedures when you're evaluating a function that is composite. Look at the inner value, simplify that inner function first, and then look at that outer function and simplify to evaluate. So let's use this example as some reinforcement. F of h of 1, let's solve for h of 1 first. Wherever you see an x, draw in parentheses and put in a 1. Simplify, and you get that h of 1 is equal to 5. And now we want to evaluate what f of 5 is. So now we're looking at our f of t. Wherever you see your t, put in parentheses and replace or fill in those parentheses with a 5. Simplify, and you get your final result to be 20, which is our f of h of 1. And we're done.
So now we have our fourth objective, which is finding the domain of a composite function. And so we have our formal definition of finding a domain of a composite function. And so the domain of a composite function f of g of x is the set of those inputs x in the domain of g for which g of x is in the domain of f. So in short, what does this mean? You want to find the domain of the input, our g of x, and then you want to find the domain of our f of g of x, and then find the intersection between those two domains. So you want to figure out what is the overlap between those two, and whatever that overlap is, that represents your domain of your composition function. This is the step-by-step procedure in how to go about it. Again, find the domain separately, and then you want to find the overlap between those domains to find your final result. So now let's practice this. We have an example 7 here. And so I'm going to create 2 columns. We have our f of g of x, which is, we're going to look at our f of x function, and wherever we see an x, we're going to put in some parentheses. Inside those parentheses, we're going to put in our g of x, and then we're going to go ahead and simplify. So 1 as a fraction with that common denominator is 3x minus 2 over 3x minus 2. 5 stays in the numerator. Our new denominator is 4 minus 3x plus 2 all over 3x minus 2. Combine some like terms, and we get 5 over 6 minus 3x over 3x minus 2. Do some keep change flip, and you end up with 5 in parentheses 3x minus 2 all over, we can factor out a 3, and then we're left with 2 minus x. Okay. And so this is our f of g of x. And I'll probably, why don't I shrink this so that it is, so we have some more white space. All right, much better. So now when we're looking at this function, what is our domain? Think, okay, domain, what are our restrictions? We can't have 0 in the denominator, it will make it undefined. And then we do not want any negative numbers underneath an even root index. Lucky for us, we don't have to worry about that second condition. That first condition, though, we do, because we have a fraction. And more importantly, that 2 minus x cannot be equal to 0. Because if it is, it makes the denominator equal to 0. So this tells us that x can't be equal to 2. Okay. However, we're not done, because we also need to look at the domain of this input function g of x. So let's write that over here. Domain of g of x. And our g of x is this whole 4 over 3x minus 2. Again, you don't have to worry about even root indices. And that's because we have no radicals in this fraction, but we do have a fraction, which means the denominator cannot be equal to 0. So 3x can't be equal to 2, which means x can't be equal to 2/3. Okay. How do we represent these two values graphically? Well, they're just 2 points that are excluded from the domain. So when we're looking at our overall domain of our composition function, it's the intersection between these two domains. And the intersection is simply the overlap of the two, and that means all real numbers except these two specific points, these two values. So graphically, we're just going to have open circles there and then shade in everything else. In interval notation, what does this look like? This just looks like negative infinity, comma, 2/3, union 2/3, comma, 2, all soft brackets because we are not including, oops, sorry. My iPad just spazzed out for a second. All soft brackets because we are not including those end values. And then union 2, comma, positive infinity. And that's it. This is our domain of f of g of x. We're done. Okay. Let's do another example together. We have example 8. Same exact process applies. We first want to find f of g of x. Wherever you see your x in your f of x, create some parentheses. And then inside those parentheses, you're going to go ahead and fill that with your g of x. And now we want to find the domain of this. Now, we have no fractions here, which is great, but we have an even root. These are square roots here with indices of 2. And so we cannot have negative values underneath the root, which tells us that we have the square root of 3 minus x plus 2 has to be greater than or equal to 0. And so we get the square root of 3 minus x is greater than or equal to -2. But that always has to be the case, and maybe we'll put a pin on this left-hand side so that you can really see how that's always going to be the case by looking at our domain of our input, which is our g of x. Again, we do not want any negatives underneath that square root, so 3 minus x has to be greater than or equal to 0, which tells us that x, if you add x to both sides, inverse operations, you get x is less than or equal to 3. So from a number line perspective, we have a filled in circle, and we're shading all values to the left. In interval notation, this just looks like negative infinity, comma, 3, hard bracket. All right. So why is this so important? Well, now let's look back on that left-hand column, and we have square root of 3 minus x has to be greater than or equal to -2. Well, if we already have the restriction that 3 minus x needs to be greater than or equal to 0, then that means the square root is always going to be greater than or equal to -2. So we do not have to worry about anything on this side because our domain on that right-hand side restricts that left-hand side to satisfy the necessary conditions. Okay, so our interval -∞, 3 satisfies these conditions. I'm going to make this a little neater. Much better. So what do we end up getting? Well, our domain of our composition our f of g of x is just -∞, 3, including 3. And we're done.
And finally, we're on our last objective, being able to decompose a composite function into its component functions. Sometimes it's necessary to compose a complicated function, aka just break it up into simpler functions. And sometimes there's more than one way to do it. So we have the freedom to do what is easiest for us and might be easy one way for me and easy another way for you, but we both have solutions to the problem. So it's kind of cool that there is more than one way or one solution when we're dealing with decomposition. And so this last example, we're gonna write a function as the composition of two functions. So we're given f of x is equal to the square root of 5 minus x squared. That square root we can break into, let's say we now have an h of x and a g of x. Our h of x can just represent the square root portion. So we'll call that square root of x. And then our g of x can represent the inside portion. Our 5 minus x squared. So f of x is essentially our h of g of x, also known as hog. And that's it. So this was the key. We broke up our f into two different functions. We decomposed them. Right. Any questions on this at all? So that does conclude our section 3.4.